Welcome to the lecture on magnetic coupled circuits. In this video, we are going to see about self and mutual inductance, and then we will see about what is dot convention, coupling coefficients, and then we will go for the examples. So what do we mean by magnetic coupled circuits? It means that if there is one coil, like you must have seen this kind of circuit in transformers. So if you have a current flowing in one coil, then what will happen is the flux will be produced, magnetic flux, and this magnetic flux uh, will be going to attach to this second coil on the secondary winding side. And if you change the current or voltage for the first winding, this magnetic flux will also change. Let me call this flux as phi 1. So since this is a first circuit, so the flux produced by this first circuit, when we apply a voltage of V1 and current I1, we will get phi 1 flux. So this some part of this flux will go to the second winding, and since it is changing, an EMF will be generated on this in this second winding. So you must have studied about this in your BTech first year. So when the flux phi is generated due to this current I1 in the primary winding, this phi 1 will have two parts. The first part, we can call it as phi 11, is actually wasted and it is of no use, and we can call it as a leakage flux. And the second flux is phi 12. This is the flux that actually goes to the second winding and induces voltage in the secondary winding. So this flux is called the useful flux, right? So not all the flux that is produced in the primary winding is useful. So we can write this phi 1 as summation of phi 11 plus phi 12, right? So what happens is, when a current I is flowing in this primary conductor, there will be a voltage generated in this coil because of the flux change, and let me call it as E1 in the primary side and E2 in the secondary side. So what will be the value of E1? E1 must be proportional to the change in this flux d phi 1 upon dt, right? So whatever the flux that is being produced in this coil, its change with respect to time should be proportional to the EMF generated. And you have already studied that it will be equal to minus N1. Suppose there are N1 turns in the primary winding and N2 turns in the secondary winding. So it will become N1 minus N1 times d phi 1 upon dt. So this equation you already know from the Faraday's laws of magnetic induction. And since in the primary winding, the whole phi 1 flux is generated, so we have taken this whole phi 1 in this equation. So let us change this equation a little bit. So we will get minus N1, and let us multiply a term d phi 1 upon di1. So I am multiplying di1 by di1 in the numerator and denominator, and so we will get di1 upon dt. So from the initial lectures of network theory, you must be remembering one formula, that inductance L is equal to N phi divided by I. Inductance L is a material property and it does not change. So even if you take in place of phi as d phi and in place of I as di, or change in phi and change in current in this equation, this formula will hold good. So this whole thing, since it is related to the primary winding, this whole thing can be replaced with, let me write it here, E1 is equal to minus L1. So what is L1? L1 is the self inductance. So self inductance is that inductance that is the inductance value um, in the uh, primary inductor itself. So it can be written as minus L1 into di1 upon dt, right? So you can see that there is a minus sign, and obviously it is because the whatever is the EMF is produced in this primary winding will try to oppose the source or the cause of it. So that is why this E1 is also called as back EMF, right? Now if we talk about E2, so you see that there is no source in the secondary side. There may be some kind of load connected to the output. So this E2 value, similar to the E1, can be written as it must be proportional to which phi will you take. This phi 12 is the value of flux that is being transferred from the primary to secondary, and this phi 11 is wasted. So you will only be taking E2 as d phi 12 divided by dt, not the whole d phi 1, only d phi 12, because phi 12 is the useful flux that is being transferred from the primary to secondary side. So E2 should be proportional to this, and if we equate it using the Faraday's laws, we will get minus. Now we will take N2 because the secondary winding is considered. So N2 is the number of turns in the secondary winding. So it will be minus N2 into d phi 12 upon dt. Now similar to the previous equations, uh, let me call this as equation 1. We can multiply E2 is equal to minus N2 into d phi 12 divided by di2 multiplied by di2 divided by dt. Sorry, not I2, I1, because there is no I2 current, there is only I1 current. So this will become di1 upon dt, right? So what will this term be called? Now, this is the inductance value in the secondary winding due to the flux produced by the primary winding. If uh, in the previous case, the L1 value was the inductance value due to the due to the flux produced in that same winding. But now, since for the secondary winding, this inductance value is coming from the flux produced by the some other inductor or other coil, then we will call this term as not self inductance, we will call this as mutual inductance. So this inductance is caused because of some flux coming from some other windings or some other wires, right? So let me call this as M21. M21 means mutual inductance of the second winding due to the flux coming from first winding. So let us replace this. So we will get equation like this: E2 is equal to minus M21 di1 upon dt. Now let's take a second case circuit. In this, we are going to apply our source to the secondary side, and then we will see how the self inductance and mutual inductance will be working. Now in this circuit, as you can see, the excitation is provided at the secondary side, and we have to see the mutual inductance at the primary side or in the E1 side, and self inductance in the E2 side. So as the previous case, here also this flux phi 2 will be produced in the secondary coil, and it will also have two parts. First part is phi 22, which is leakage, and second part is phi 21. So this is your leakage flux, and this is your useful flux, right? Now let us write quickly those same equations as we did before. So in this case, similar to the previous one, we are going to get E2 will be equal to minus N2 d phi 2 upon dt. So on rearranging this and multiplying and dividing it with di2 upon di2, uh, we will get finally minus sorry, N2 into d phi 2 upon di2 into di2 upon dt. So this whole thing can be replaced as L2 because the L2 is the self inductance and it is the inductance caused by the flux produced in the self coil or in its own coil because of some current. So we can write this equation as E2 is equal to minus L2 di2 upon dt. So this is your equation 1. And similar to the previous case, we will get E1 as minus M12 di2 upon dt. So here you can say that this M12 value is nothing but d phi 21 divided by di2 multiplied by N1. So M12 is the mutual inductance in the primary coil due to the flux coming from secondary coil. So this you can call it as your equation number 2. So this is how these mutual and self inductances work. And now let us move to the next slide. Now let us talk about dot convention. The dot convention comes from the style by which we wind our coil. So suppose you have an inductive coil like this, right? So if a current is entering like this, it will go in this direction, then here, then here, then here. So can you tell me where will the direction of flux will be? uh, like this. Okay, so if you use the right hand rule, you can see that the current will be if the current is moving like this, sorry, if the current is going in the thumb's direction, you will have flux moving in the the movement of your right hand direction. So if current is moving upward, your flux will be moving circularly around this current. So if the current is going in this direction, like this, so can you tell me where will be the flux? If the current is going in this direction, suppose this pen is like this, and if current is going in this direction, so your flux will be moving like this. So using this right hand rule, we can say that the flux is going like in this direction, right? So because of all these coils, this flux will become strong and it will go in this direction. Now let us do a little bit of change in this circuit, and in place of rotating this circuit in this way, let us rotate this circuit in this way. Now I am rotating it in anti-clockwise. So in the previous case, I had rotated it in the clockwise direction. See my hand in the video. In the previous case, I had rotated it like this. But in this case, second case, I am rotating it like this. So now the rotation methodology is changed. Now let us again enter the current in the same direction. But now, since the current is moving like this, like this. Now, can you tell me what will be the direction of magnetic flux? Now the current is in the coil is moving in this direction. So the magnetic flux will now be moving like this, like this. So now the overall magnetic flux lines will be coming like this. So the direction of magnetic flux is now towards upside of the coil. So just by making a little change in the making of the coil method, the direction of magnetic flux is changed. So if the direction of magnetic flux is changed, definitely the voltage produced or the back EMF we talked, E1 and E2, the direction of that will also change. So that is why the sign of this mutual inductance will also change. If this flux is causing some voltage produced in some other circuit, or mutual inductance, uh, because of this winding, the value, the sign of the voltage and the sign of mutual inductance will change. So let us make a few circuit to understand how we will solve our questions using dot convention. So suppose a winding is given. In the questions, generally you will not be able to see by which method, either clockwise or anti-clockwise, the winding is done. So dot convention is used. So if suppose there is a dot here and there is a dot here, and if the self inductance of this coil is L1 and this is L2, one thing I forgot to tell you in the previous slide, that the mutual inductances that we got here in the second case circuit we got M12, and in the first case circuit we had got M21. So for the same circuit, this mutual inductance M21 will always be equal to M12, because whatever is going to be transferred from the primary side to the secondary side, similar transfer will be happening from the secondary side to the primary side. So for a same circuit, same coupled circuit, the mutual inductance always remain the same. So this M12 and M21 for both these circuits, case 1 and case 2, which are basically similar, will remain same, and we can call them just as M. So mutual inductance for these two coil will always be same, and it will be M, right? So coming back to here, uh, let us call that the mutual inductance between these two coils is M. And if current is entering on this dot is here and the current is entering on this dot I1, and suppose if there is a current I2 which is entering on this dot, so we can say that the sign of this mutual inductance M will always be positive, because both the coils are having a current which are entering the dot. So it means that the flux produced will be supportive. So we can actually visualize this thing using one special circuit. Let me draw it for you. So in this magnetic circuit, it is basically a transformer in which these two squares are representing magnetic circuit. You can see that in the first coil, due to this current I1, there is a flux being produced and it will be going in the upward direction. So this flux will be going here in this direction, and due to the secondary circuit, the flux is again going into the upper direction, and it will go towards this direction. And you see that both these fluxes are in opposing direction, so these fluxes will subtract from each other, and that is why reduce the overall inductive value of these coils. So in this case, the mutual inductance M between these two coils will have a negative sign. And where will this negative sign will come? So if you are calculating the total inductance value of the primary coil, so suppose it has self inductance as L1, and suppose the secondary coil has self inductance as L2. So the total inductance of this primary coil will not only be L1, but also it will be because of some inductance, which is M mutual inductance, produced by the flux coming from the secondary coil. So since these fluxes are in opposing direction, we can say that the total inductance or L equivalent of the primary winding, let me call it as L equivalent 1, will be equal to L1 minus M. Why M? Because these fluxes are opposing each other. Similarly, on the secondary side, the inductance value of secondary side will be L2 minus M, right? So here also the overall L2 inductance value will be decreased by M. So we can say that if we want to represent this circuit in the dot convention, we can simply write this like this. So the current at I2 is going in this direction. So now we can say that if the current is coming in the dot for primary circuit, and for the secondary circuit, if the current is going out of the dot, then in that case your M will have a negative sign for both the coils, right? And as opposed to that, if both the dots are having current either coming inside or either going outside, in that case your mutual inductance M will be having positive signs. So let us write down all these cases. So you can see the four cases of these mutual inductance circuits. So in the first circuit, you can see that both these currents are entering at the dot. And here also you can see that both these currents are exiting at these dots. So for both these circuits, the equation for V1 will be uh, L1 di1 upon dt plus sign. Why am I taking the plus sign for mutual inductance? Because due to the in the dot convention, in for both the dots the current is either entering or either going out. So for both these circuits 1 and 2, we will have V1 is equal to L1 di1 upon dt. You know the voltage across inductor is L di by dt, and plus mutual inductance M, and this mutual inductance in the primary circuit is because of the current flowing in the secondary circuit. So it will have an equation like M di2 upon dt, not di1, because this mutual inductance value M is caused by the secondary windings flux, right? So we have already studied it. And similarly V2 will be L2 di2 upon dt plus M di1 upon dt. And since both these since this circuit is same, either you excite it from the primary side or the secondary side, this mutual inductance M is going to be the same for both the cases. Now here in the third and fourth case, you see that here at this dot the current is entering, but at this dot current is exiting. So these are opposing in nature. So here the mutual inductance M will have a negative sign. And similarly here there is a dot here, current is entering, but if you see on this dot, the current is exiting. So for this also the M will have negative sign. So for this we can write the equation V1 is equal to L1 di1 upon dt minus M di2 upon dt. This is your equation for V1. And similarly for V2, we will have L2 di2 upon dt minus M di1 upon dt. So this is how you will write KVL equations in the magnetic coupled circuit. So now you have to consider the mutual inductance value also. And what is the mutual inductance? It is the inductance caused in a particular coil or inductor because of the flux coming from some other coil, right? And if the inductance value is because of its own flux, then it is called self-inductance. And if the inductance is caused because of some flux coming from outside, then it is called mutual inductance, right? Now, there is a term called coupling coefficient or coupling factor. It is represented by K, and it is given as the ratio of useful flux to the total flux produced in any coil. So coupling coefficient or coupling factor is the ratio of useful flux to the total flux. So we have already seen this kind of circuit. So this was having self-inductance L1, this was having L2, some mutual inductance M. Uh, it was having a coil turns of N1, this was having turns of N2. This was having a current I1 and this was having a current I2. So we saw that in the previous case that if the first coil is producing a flux phi1, so it will have two part, phi11 which is leakage and phi12 which is the useful flux. And similarly the secondary coil, if it is producing a total flux of phi2, it will also have a leakage flux phi22 and useful flux phi21. So for the primary case, let me call its coupling coefficient as K1. So for the primary case, your K1 will be useful flux, which is phi12 divided by total flux phi1. And similar to that, for the secondary case, let me call its coupling coefficient as K2, and K2 will be phi21, which is useful flux, divided by phi2, which is total flux. So um, K1 is this and K2 is this. Now, for a same pair of coils, which is this the case, this K1 like M12 and M21 was always same for the same pair of coils. Similar to that, for the same pair of coils, K1 will also be equal to K2, which we can call as K. So for any pair of coil, the coupling factor or coupling coefficient for the primary coil or the secondary coil is going to be same, which is similar to the mutual inductance value in the primary and secondary coil. So M21 will also be equal to M12, which is equal to M. So this we have already seen. Uh, now let us move further and do some mathematics to relate these K value, M value, and L1 and L2. So you already know that M21 is equal to what was the value of M21? M21 is the mutual inductance in the secondary coil due to the flux coming from primary coil. So M21 can be called as N2 phi 12 divided by I1, right? So this is your equation 1. Similarly, M12 can be called as N1. M12 is the mutual inductance of the first coil due to the flux coming from second coil. So this can be written as N1 multiplied by phi 21 divided by I2. Yes, okay. So this is your equation 2. Now, if we multiply this equation 1 and equation 2, what we will get? M12 into M21 will be equal to N1 phi 12 upon I1 multiplied by N2, sorry, this is N2 phi 21 divided by I2. So since you know that M12 and M21 are same, and they both can be represented as M, so this will become M square is equal to N1 phi 12 divided by I1 multiplied by N2 phi 21 divided by I2. So let us do some rearrangement and uh, try to convert this into the some known forms. So you know that, and you already have N1 and I1 here, right? What I have done is I have actually rearranged. Like if you had multiplied M12 and M21 in one part, you were getting N2 upon I2 into phi 12. So in place of that, uh, I have actually written as N2 into phi 21 upon I2, right? So I have actually replaced in the multiplication, this I1 should be here and this I2 should be here. So you can just replace it na, so that it will become in some more familiar form. So that is what I have done. This N1 upon I1 you have. So what is the thing that you should multiply in this equation so that it becomes in some known form? So you know that L1 is equal to N1 phi 1 divided by I1. So you must have to multiply phi 1 in the numerator and denominator. Similar to that, in the secondary coil, in this place, you have to multiply phi 2 in the numerator and denominator. So by doing that, we will have N1 upon I1 into phi 1 multiplied by phi 1 2 upon phi 1. So this phi 1 is multiplied in numerator and denominator. And again, this thing is multiplied by N2 upon I2 multiplied by phi 2 into phi 21 divided by phi 2, right? So what is this? This is nothing but L1. What is this? This is nothing but L2. And can you tell me what is this and this? So this is nothing but your K values. So this was K1 and K2 and both are same. So these are your coupling factors K value. So you will finally get M square is equal to K square L1 L2, or you can say that the mutual inductance will be equal to K times under root L1 L2. So for any pair of coils, this relationship always holds. Now let us quickly see some circuit combinations and see how their inductance value will behave. So suppose you have two coils in series and there is a current I going in it, and the dot convention is given like this. So suppose this first coil is having self-inductance L1, this is having L2, and these both are having a mutual inductance of M. So you see that this current is entering both these coil at the dot end. So here this current, same current will go and it will enter at the dot end. So this M will have a positive sign. So if you want to write a KVL equation for this circuit, so you can write it as, let us write KVL. So we can write Vt is equal to L1 di upon dt plus M mutual inductance times. Now this mutual inductance M in the first coil is because of the flux produced in the second coil. But since the current is same in the second coil also, we will have the same current di upon dt. So in the second coil also the same current I is flowing. There is no I1 and I2. There is only one current I. So this mutual inductance will also produce a voltage drop because of that same current, but because of the flux produced in the second coil. So this is the first part. This is only for the first coil. Now you have to add the voltage drops in the second coil also. So it will be L2, again the same current di upon dt. Now again you have to add this term M, mutual inductance, the mutual inductance in the secondary coil due to the flux produced in the primary coil. So this mutual inductance terms, you remember, will have to come two times in the circuits like this. So you will have M di upon dt. So you can directly write Vt is equal to, let us take di upon dt common. So you will have L1 plus L2 plus 2M. So for a circuit like this, if the two inductors are in series and having the same dot convention, their equivalent inductance value will be the summation plus two times the mutual inductance. So for a circuit, for a case one circuit like this, uh, series circuit like this, you will have L equivalent is equal to L1 plus L2 plus 2M, not 1M, 2M, you remember this, because the mutual inductance is caused in both the windings because of the other winding. Now let us see the, quickly see the second circuit. So here also we are taking series of two inductances, L1 and L2, but now if the dot is here, for the second let us take the dot here. So if the current is entering here, on this dot the current is exiting. So now the mutual inductance will have a negative signs, and L equivalent for this circuit will be L1 plus L2 minus 2M. You remember, now it will have minus 2M. Okay. Now quickly see the formulas of some parallel combinations of two inductors. So suppose if there are two inductors in parallel like this, L1, L2, both are having dots here, and let us say that there is a mutual inductance M between these two coils, and obviously there will be two currents I1, I1 and I2 entering in these two coils, and since this is in parallel, the formula you have to learn, you can derive it, but I'm just going to write the formula. The L equivalent will be equal to L1 L2 minus M square divided by L1 plus L2 minus 2M. So this formula you have to remember, although it comes very seldomly in any exam, but you can remember this formula. So now let us see the last circuit, which is parallel opposing two inductors. So here, as you can see, if the dot is here, let us take for secondary coil dot here, and they are having mutual inductance M, self inductance L1 and L2, current I1 and I2. So for this, I am just writing the equivalent uh, inductance value formula as this. L equivalent is equal to L1 L2 minus M square divided by L1 plus L2 plus 2M, right? So for this fourth circuit, we will have L equivalent this, and for this third circuit, we will have L equivalent this. So only difference is in the denominator there is negative sign, and here it is positive signs. Rest is same. Now let us see equivalent circuit of transformer. So if a transformer is given, we can actually draw an equivalent circuit for transformer, and let us see how it looks. Now we have transformer. In first case, we are having uh, supporting flux or supporting mutual inductance, which will have a positive sign, and in the second case, we are having non-supporting or opposing flux, so it will have a negative mutual inductance sign. So the equivalent circuit for these transformer, as you can see, these two lines actually represent magnetic circuit. So for solving in normal network circuits, we have to convert it into equivalent circuit. So uh, between these terminals, let me call this as AB and this as PQ, we will get an equivalent circuit like this. So this is the same terminal AB and this is as PQ. So we will a circuit like this, and its values for the first case will be L1 minus M, L2 minus M, and this will be M. So this will be the equivalent circuit, and for the second case, it will have L1 plus M, the second coil will be L2 plus M, and this will be minus M. In place of M, this is going to be minus M. So this is the opposing case. Now there is a term, the energy in the inductors. The total magnetic energy is stored in the inductor. So you already know that total energy in the uh, inductor was 1 by 2 Li square, where L is the inductance and I is the current flowing through that inductor. So in these circuits, um, you know that there are two coils L1 and L2, and also there is an mutual inductance M. Uh, the total energy will be stored in L1 and L2, and also in the this mutual inductance M also. And in the first case, if it is opposing, the mutual inductance energy will be added, and since in the second case the fluxes are opposing each other, they are cancelling out each other, the mutual inductance energy component will be subtracted. So we can write the total energy in this combination, this transformer will be 1 by 2 L1 I1 square uh, plus 1 by 2 L2 I2 square. So this is in the first winding because of its self inductance, and this is in the second winding. And then we will have plus minus sign. So I'll tell you when will it be plus and when will it be minus. So M times not I1 or I2 square, it will be I1 multiplied by I2. So since the mutual inductance is caused by both these I1 and I2 currents, so we will have to take uh, the multiplication of I1 and I2. So this will be plus for the case 1 circuit when the circuit is supporting or fluxes are being added, and this will be the for the case 2 circuit. Negative sign will be for the case 2 circuit. So this is the total magnetic energy stored in this transformer, right? So you have to remember this formula. Now let us do some examples. In this first example, we have to find the total equivalent inductance value between the terminals A and B. So you see that there are three coils of having self inductance of 20 Henry, 10 Henry, and 9 Henry. There are mutual inductances between the first and second coil and the first and third coil, but there is no mutual inductance between the second and third coil. And you also see the dot convention. So if the current is entering in this direction, For the first two coils, the direction will be same, but for the third coil, the direction will be opposite. So I think you can very easily say the L equivalent value. So let me call this as L1, call this as L2, and let me call this as L3, and also the mutual inductance between first and second coil, let me call it as M1, and between first and third, let me call it as M2. So your L equivalent is definitely going to be L1 plus L2 plus 2 times M1, obviously because they are supporting. The current is entering in the both the coils in the dot, then plus L3, and for the L3 uh, we will have to add two, not add, because the dot is on the other side, so current is exiting from the third coil's dot side, so we will have to take a negative sign, and it will be 2 times M2. Why 2 times? Because the first mutual inductance will be in this 9 Henry inductor because of the first coil, and also in the first coil there will be a mutual inductance of M2 due to the third coil. So finally we can write our L equivalent as 20 plus 10 plus 2 times 2 plus what is L3? 9 minus 2 times 1. So this is how we can solve it, and finally we will get how much? So 20, 10, 30, and 39 plus 4, 43 minus 2, 41. So total 41 Henry. So you can check it, right? Let us go for the second example. So in the second example, we have to find the value of K, which is coupling factor between these two coils under resonance condition. So this is a series RLC circuit, and you know that under resonance condition, the capacitive impedances cancel out the inductive impedances. So the total value of XC should be equal to total value of XL equivalent. So whatever is the equivalent uh, inductance value. So what is your XC value? It is total J15. And what is your total inductive value? So let me say that there is a mutual inductance M between these two coils, and since the current will be entering in both the coils at dot, this M will be supportive. So you know that XL value is the magnitude of, I mean, XL is omega times L, right? So let me take this omega frequency at which this voltage or current is operating in this circuit. So for the first coil, this omega L is given as 6. For the second, this omega L is given as 7. So let me call this value for M, XM, as XM. So we will just put it as XM, right? So this total J15 should be equal to J times 6 plus 7 plus XM. So XM is the impedance value of, or inductive impedance value due to this mutual inductance M. So I think you understand this 6 value is not the L value. It is basically the multiplication of omega and L, which makes it impedance in the impedance form, which is the 6 ohm. So the unit for these things are basically ohm only, right? So you can cancel out J from both the sides. So I think it is clear that under resonance condition, the capacitive inductance, which is J15, and the inductive impedance, which is the summation of all the inductive impedances like J6, J7, and because of this M, let me call it as XM, should be equal. And don't worry about the negative sign. Obviously, if this is negative and this is positive, then only the summation is going to be cancelling out each other. So using this, you will get XM is equal to 2 ohm, right? So you got your impedance value due to this mutual inductance as 2 ohm. Now, since you have to calculate the value of K, What do you have? You have only this formula, uh, uh, m sorry m is equal to k times under root L1 L2. So we have already studied this. So since in this form you do not have the values of L1 L2 and m, rather you have the values of impedances caused by L1 L2 and m, which is 6 ohm, 7 ohm, and now 2 ohm you have just calculated. So what you will do is you will multiply both sides by omega in this equation. So you will get omega m is equal to omega, or rather let me write it as k into omega under root L1 L2. So if you take omega inside, it will become omega squared. So you can write omega m is equal to k times omega L1 into omega L2, right? So this is nothing but your xm value is equal to k times under root, this is your xl1 multiplied by xl2. So what is your xm value? You just calculated, it is 2 ohm, and you have to calculate k multiplied by your xl1 is 6 and xl2 is 7. So here xl1 is 6 ohm and xl2 is 7 ohm. So this is 6 into 7. So by calculating this, you can easily find k is equal to 2 divided by under root 42. So this is the coupling factor or coupling coefficient for the given circuit, right? So this is how you can calculate k. I think I made a little mistake here. It is a very common mistake. Uh, you know that L equivalent is equal to L1 plus L2 plus 2m, right? Not single m. So in place of xm, here we will have to take 2xm, right? 2xm. So 2xm is 2 ohm. So it means xm will be equal to 1 ohm. So this is a small difference. So here in place of 2, you will have to write 1. So your answer will be 1 upon under root 42. Clear? So sorry for this mistake. This is a silly human mistake. So in today's last example, we have the circuit and we have to calculate the equivalent inductance value from, if we see the from the terminal A and B, and you can see that on the secondary side the circuit is short circuited. So whenever you apply an excitation from A and B, a flux is being caused, and because of this flux, there will be a voltage generated like this, and there will be a current created. So if suppose if the current direction is given like this and current produced at the output is given like this, you see that this is in the opposing flux formation. So the fluxes in the two windings will oppose each other. So we have already discussed about the equivalent circuit for this kind of transformer. So since we have to find the L equivalent, we have to convert it into the equivalent circuit. So what was that equivalent circuit? It was like this, right? Sorry for my drawing and writing skills, it is very bad. So for for opposing fluxes, your mutual inductance will have minus m here, and this was your L1 minus, was it minus or plus? I think it was plus. So it was L1 plus m, and this was L2 plus m, right? And this was your A and B, and the output is short circuited, right? So let us quickly put the values. What is your L1? It is 10 Henry, L2 is 2 Henry, and M is also uh, 2 Henry. So we will have the first coil will have 10 plus 2, which is 12 Henry. Then 2 plus 2 is 4 Henry, and this minus M means minus 2 Henry. So you have a simple circuit like this. 12 Henry minus 2 Henry and 4 Henry. So now I think it is very easy for you to calculate the L equivalent. So L equivalent will be equal to 12 plus 4 into minus 2 divided by 4 plus minus 2. So you will finally get L equivalent as 8 Henry on solving this. Thank you very much.